Welcome everyone to the problem solving session of the thermodynamics course from NPTEL. Myself Pradeev E, I am one of the TA of this course. Today we will solve some problems using entropy concepts, and then finally I will start some problem with exergy or availability concept. So the first problem is on the screen. A fluid undergoes a reversible adiabatic compression from 0.5 megapascal 0.2 meter cube to 0.05 meter cube. According to the law, PV power 1/1.3 is equal to constant. Determine the change in enthalpy, internal energy, entropy, and the heat transfer and work transfer during the process. So we have been told that there is a fluid that undergoes a reversible adiabatic compression process. So if we draw this process in a PV plot, during compression the pressure increases and volume decreases. So it should resemble something like this, starting from 1 to state 2. Here this curve PV power 1.3 is equal to constant. Now P1, the initial state is given as 0.5 megapascal, and the initial volume is also given as 0.2 meter cube, and the final volume is also given as V2 is 0.05 meter cube. Now we need to calculate some parameters such as enthalpy, internal energy, entropy, heat transfer and work transfer. We can start with calculating the final pressure. Here the based on PV power 1.3 equal to constant, we have P1 V1 power 1.3 is equal to P2 V2 power 1.3. So with this we will get as P2 as P1 into V1 by V2 the whole power 1.3. So this is 0.5 megapascal into V1 by V2 is 0.2 by 0.05, the whole power 1.3. So that means P2 can be calculated. So this is 3.03 megapascal. Now we can calculate the enthalpy. We need to calculate the change in enthalpy. So delta H is equal to integral dH, and we know H is given by VdP. Here from this expression we can calculate V as P1 V1 power n divided by P the whole power 1 by n. So substituting the value of V in this expression, we have P1 V1 power n. So this is a P1 V1 power n is a constant, so this can be taken out of the integration, and within the integral we have dP divided by P power 1 by n. Integrating this, we will get P1 V1 power n into so this is from 1 to 2, so we will have P2 power 1 minus 1 by n minus P1 power 1 minus 1 by n whole divided by 1 minus 1 by n. Now writing the expression again. So 1 minus 1 by n is n minus 1 by n. Solving this, we will get n minus 1 P2 V2 minus P1 V1. So this is the enthalpy change. Now we know that n is 1.3 divided by 1.3 minus 1, and final pressure is 3.03 into 10 power 6 into final volume is 0.05 minus initial pressure is 0.5 megapascal, so 0.5 into 10 power 6 into V1 is initial volume is 0.2 meter cube. So this is 223.17 into 10 power 3 joules, or this is 223.2 kilojoules. So now we have calculated the change in internal energy. Next is to change in enthalpy of the system. Now next we can calculate the internal energy, entropy and others. So to calculate internal energy, we have writing this expression H is equal to U plus PV. So that means H2 minus H1 is U2 plus P2 V2 minus U1 plus P1 V1. So this we can have U2 minus U1 plus P2 V2 minus P1 V1. So change in internal energy del U is U2 minus U1. So that is H2 minus H1 plus P1 V1 minus P2 V2. So H2 minus H1 is already calculated, and that is 223.2 into 10 power 3 plus initial pressure P1 is 0.5 megapascal into V1 is 0.2 minus P2 is 3.03 megapascal into V2 is 0.05. So internal energy can be calculated like this. This is 171.7 into 10 power 3 joules, or 171 kilojoules. So we have calculated the change in enthalpy and change in internal energy. It was said that it is undergoing an reversible adiabatic process. So as given in the problem, it is undergoing a reversible adiabatic process. So that means there is no heat transfer. So that means Q is equal to 0. We know Q is equal to T ds. So that means change in internal energy ds is also equal to 0. And writing the first law expression, we had Q is equal to change in internal energy plus work done. So here Q is 0. That means work done is equal to minus of delta U, and that is minus of 171.7 kilojoules. In this problem, the work is done on the system to compress a fluid. So that means work is done on the system. So generally we take work done by the system as positive. So here work is applied on the system. So that's why we are getting a negative value for work done. And because of applying work on the system, we get change in internal energy which is positive. That means the final internal energy is greater than the initial internal energy. Do you have any questions in this problem? Sorry, my handwriting is not so good today. Maybe generally it is not so good. Today it's even worse because I didn't get the proper touch screen today, so I have to use a different one. Mr. Sahu George, if you have any question, you can ask me.
No sir, I understood. No sir, no question, I understood.
Yeah, okay, thank you. So in the next problem, we have entropy generation during a throttling process. Steam at 7 megapascal and 450 degrees Celsius is throttled in a valve to a pressure of 3 megapascal during a steady flow process. Determine the entropy generated during this process and check if the increase of entropy principle is satisfied. So throttling process means a fluid at a high pressure is open to a low pressure system, and it is freely made to expand without any work being extracted. So during this process the internal energy remains the same, and that is how we should go through the problem. So now we know P1 is equal to 7 megapascal and T1 is 450 degrees Celsius, and for P2 we know it is 3 megapascal, and we know that H2 internal enthalpy at the final state is same as the initial state because it is only undergoing a throttling process. So now for this we can get the enthalpy and entropy values for the state 1 from the steam tables. So H1 so it was 7 megapascal and 450 degrees Celsius. Here we have megapascals and saturation temperature. So between 4 we have 6 and 8 megapascals, and for this the saturation temperature is only 275 and 295. So that means at 7 megapascal the saturation temperature will be somewhere around 285 degrees Celsius, but our initial state of the steam is at 450 degrees Celsius. That means it is a superheated steam. So to find the properties of that, we need to go to the superheated steam table. So for the 7 megapascal we have the table here. Here for temperature of 450 degrees Celsius, the properties are given here. So for 7 megapascal and 450 degrees Celsius of the superheated steam, the enthalpy is given as 3288.3 and entropy is 6.635. So we will note down this. So enthalpy is 3288.6 kilojoule per Kelvin, and entropy is 6.635. This is kilojoule per kg Kelvin, and I think this is 3288.3. Just 3288.3. So now we know that the final state, the pressure is 3 megapascal, and we know that enthalpy is same as this, which is 3288. We can see if it applies in it exists in the superheated state or the saturated state. So here we have for the 3 megapascal, and for enthalpy of 3288 it is somewhere between these and this. So the final temperature is somewhere between 400 and 450 degrees Celsius. To calculate this, we have to note down. So at 400 we have 3231.7, and at 450 degrees Celsius we have 3344.8. Now what we need is 3288.3. So for this we can calculate the temperature. So this is 425 degrees Celsius. So it is almost in the half. So how I got this is by by doing linear interpolation. So we have this line equation y minus y1 by y2 minus y1 is x minus x1 by x2 minus x1. So here x, I can take x, this is x and this is y. So this will be the initial state, this is the final state 1 and 2. Then I have y minus y1 is 400 degrees Celsius divided by 450 by 400 minus 400. This is equal to these values, like x is 3288, x1 is 3231.7 and x2 is 3344.8. So by this I can calculate y, and That's how I calculated. It has 425 degrees Celsius. So now I know that T2 is 425 degrees Celsius, and I can calculate S2. For S2, I have these two values at 400 and 450 degrees Celsius, which is 6.923 and 7.086. Since the temperature is the midpoint of this, I can just take the average of these two, and that will be the linear interpolation. 6.923 plus 7.086 by 2, which is 7.0045. I will write down. So here we had 6.923 plus 7.086 by 2, and this is 7.0045. So we have calculated the entropy at the second condition, which is around 7 kilojoule per kg Kelvin. So now we need to determine the entropy generated during this process and check if the increase of entropy principle is satisfied. So okay, I can calculate S2 minus S1. S2 minus S1 is 7.0045 minus final entropy minus initial entropy. Initial entropy is 6.635. So this is 0.3695 kilojoule per kg Kelvin. So that means the entropy generated is a positive value here. So entropy is being generated, not destroyed, and based on the principle of increase in entropy, this we can say that this process is feasible. I hope this problem is clear. If you have any doubts, you can ask now. Moving on to the next problem. It is about entropy generated when a hot block is dropped in an ambient reservoir. So we have a 50 kg block of iron casting at 500 Kelvin, which is thrown into a lake that has a temperature of 285 Kelvin. The iron block eventually reaches thermal equilibrium with the lake water. Assuming an average specific heat of 0.45 kilojoule per kg Kelvin for the iron, determine the entropy change of the iron block, the entropy change of the lake water, and the entropy generated during this process. So we have a mass of iron at 500 Kelvin, and this is put in a lake water, and this lake is at 285 Kelvin. So heat is getting transferred out of the system. So now to find the entropy change, we have the expression delta S is equal to integral del Q by T. So for our for the first question, we have to find the entropy change of the iron block. So our system is the iron block. For the iron block, the initial temperature is 500 Kelvin, and final temperature at equilibrium, it should be the same temperature as the lake. So final temperature should be 285 Kelvin. Since it is a lake, we can assume that there is no appreciable change in temperature of the lake because of this small iron block in the lake, and we can assume that lake temperature is constant of 285 Kelvin. But the mass of the iron block temperature keeps on reducing, and so we have to calculate this using the integral. For delta Q, we have mc into dt by t, over the integral. Here we can mass will be constant throughout the process, and we can assume average is a specific heat of 0.45, so that is also constant during the temperature change. So this can be written as mc into ln of, so this changes from state 1 to 2. So I write integrating dt by t, I have ln of t2 by t1. So this is m is 50 kg into c is 0.45 kilojoule per kg Kelvin, and ln of t2 by t1, where t2 is 2.
Hello, sir. Sir.
Yes.
Sir, sir, it is the same problem worked out by our professor and sir. Only value is changed. Everything is worked out in the class. Total problem 1 in week 9.
Okay.
Same problem he worked out. Only value instead of iron, he used aluminium, and instead of 50 kg, he used 40 kg.
Okay.
Okay. Just for awareness, I mentioned only.
Oh, okay. Thank you. I didn't go through the assignment problems thoroughly, so I didn't know exactly what was.
Yeah, it is a week 9 tutorial first problem. He explained.
Okay. Thank you.
Okay. Thanks.
Okay, then I will quickly go through this, and we can go through the next problem. Yeah, so T2 is 285 and T1 is 500, and that's how we can calculate this. So this is minus 12.65 kilojoule per kg Kelvin, and entropy of the entropy change in the lake water. For the lake water, we have delta S is equal to Q by T. Here, that since the temperature is not changing, I can directly have it as Q, and this is mc into delta T by T. And here that temperature is of the temperature of the lake water, which is 285 Kelvin. Mass of the block is 50, and C is given to be 0.45, and temperature change of the block is 500 minus 285. So this is 16.97 kilojoule per kg. Sorry, it's kilojoule per Kelvin, because we have already multiplied with the mass. So the entropy change of the lake is positive, because it is heat is getting added to the lake, whereas for the iron block, the entropy change is negative, because heat is removed from the lake, from the iron block. So now if you want to calculate the total entropy generation, is total, this is 16.97 minus 12.65. So this is 4.32. I hope this problem is clear. Moving on to the next problem. We have a hypothetical device which is supplied with 2 kg per second of air at 4 bar and 300 Kelvin. Two separate streams of air leave the device, as shown in the some figure was given. Each stream is at ambient pressure of 1 bar, and the mass flow rate is for the same for the both stream. One of the exit streams is said to be at 330 Kelvin, while the other is 270 Kelvin. The ambient temperature is at 300 Kelvin. Determine whether such a device is possible. So if you have to draw the schematic, we have a device which is supplied with 2 kg per second of air at 4 bar and 300 Kelvin. So now this is getting split into 2 streams, and each stream mass flow rate is same. So 2 kg per second is split into 1 kg per second each, and for both are at 1 bar atmosphere, and for one stream the temperature is 330 Kelvin and the other stream is 270 Kelvin. To find whether such a device is possible, we can find the entropy change of the system, and if the entropy change is positive or at least 0, we can say it is possible. Otherwise such a device cannot exist. So to calculate entropy change for this, we have TDS is equal to Q, and we know Q is delta U plus W. For this system we need to write in terms of enthalpy, so I will directly write the enthalpy expression. So this is dH plus V dP, and now I know ds is equal to dH by T plus V by T into dP. Now I can rewrite dH as Cp into dt divided by T plus from equation of state I can simplify this. So we have PV equal to RT, and then V by T will be R by P. So I can have R into dP by P. So to calculate the change in entropy, I have delta S is the integral over ds. This is Cp integral of dt by T plus R into integral of dP by P. So we have Cp into ln of T2 by T1 for process varying from state 1 to 2, and plus R into ln of P2 by P1. This way I can calculate, so using this expression I can calculate the change in entropy for both the streams. So I write this as stream 1, this is 2 and this is 3. So to calculate delta S 1, 2, 3, which is S3 minus S1, we have Cp into ln, I would start with the 1 to 2, so ln T2 by T1 plus R ln of P2 by P1. So we know Cp of the air is 1.005 into ln of T2 for the stream 2 is 330, and for stream 1 it is 300 Kelvin. So we have 330 by 300 plus R is 0.287 ln of P2 by P1. P2 is 1 bar and P1 is 4 bar. So we have 1 by 4. So I can calculate this value. So this is minus 0.302, sorry, yeah, kilojoule per kg current. Sorry, I think I should have a negative sign here. Okay, how I got negative is, we had Q from the first law. We know Q is delta U plus P dV, and we know H is equal to U plus PV, and that means delta H is equal to delta U plus P dV plus V dP, differentiating the expression. All these are dH, and now we have Q is equal to, so calculating du from here, we will have delta H minus P dV minus V dP. So this represents delta U, and then we had P dV. So that's how it becomes delta H minus V dP. So this is Q, and Q is TdS, and this is where we started the problem. So we have minus and minus. Yeah.
I have a doubt, sir.
Yes.
In previous slide, in question, what they ask, sir, means I not get what is they are asking. If determine whether a device is possible, means what we can identify, sir?
Okay. So such problems comes because there could be some claims from some people, some research or scientist or someone who claims that he can make a device which will generate energy without any source input of energy, or he can claim that his heat engine or something is more efficient than other people. So in those cases, then we can use in second law, we can analyze if it is really theoretically possible. So this is one kind of problem where they have given that there is a device, hypothetical device, where the input is 2 kg per second of air, and input condition is 4 bar and 300 Kelvin, like I have drawn in the schematic. And the output of this device are the two streams of air. In one stream we have 330 Kelvin of air, and in the other stream we have 270 Kelvin of air, and each has the same airflow rate. So that means input 2 kg per second is split into 1 kg per second and 1 kg per second to the each stream, and both the output stream are said to have the ambient pressure of 1 bar. So we know the inlet condition and the outlet two outlet conditions. We need to calculate, we need to check if such a device is possible which can take in 4 bar in and 1 bar out with these temperature changes. So this can be done using second law, where we calculate entropy change of the entire system, or the entropy change of the fluid that is going in and coming out. And if the entropy change is positive, we can say that yes, this device is possible. If the entropy change is negative, which is not possible, like with any process we cannot have a entropy change of negative throughout the system. Like if the system is undergoing negative entropy change, then that means the universe should be having positive entropy change. In this system, there is no change in the ambient. It's only the some air is going in and some the same air goes out after some process with some temperature change. So looking at the entropies of these 3 points and the change in entropy of the stream 2 and stream 3 when compared to 1, we can say if such a device is possible. Did it make sense?
Okay, sir. Understood. Sir, I wondered, means in output the exhaust air means the both are equal, sir. The change in entropy means is there any difference in between the 3 and 2?
Yeah, there is temperature is different for stream 3 and stream 2. For stream 3 it is 270 Kelvin and for stream 2 it is 330 Kelvin.
Okay, when we mention it is a positive enthalpy, means entropy is a positive, then we conclude what it is.
If the entropy change of the entire system is positive, then we say that such a system is possible. It's possible to construct such a system.
Okay, sir.
Yeah, if it is negative, we can say that such a system is not possible at all. Like someone says I have a someone says I have air at 30 degrees Celsius and I feed into a system, and this is a black box for me currently. This system does something and gives out 0 degrees Celsius, and they says it is insulated and there is no heat transfer. Like there is no heat transfer is 0 through the system, and work transfer to the system is also 0, and say this is at 1 bar and output is also at 1 bar. We know that this is not possible because air cannot just like that change the temperature on its own. We have to have a refrigeration system and apply some work to the compressor where it undergoes that Carnot cycle, reverse Carnot cycle or refrigeration cycle, and only then we can reduce the temperature of the air. So this is one kind of a system, and in the problem we are given that initially it is 4 bar inlet and say 300 Kelvin inlet, and it goes to 2 streams. One is, both are at 1 bar, but one is at 330 Kelvin and other is at 1 bar and 270 Kelvin. So we will calculate the entropy at state 1, state 2, state 3, and we say S3 minus S1 is the entropy change of on this route, and S2 minus S1 is the entropy change in this route, in the top route, and then we can add up both, and then we should have the total change in entropy. If this is positive, then we say the system is possible. So here also if you calculate entropy, say this is say something like 200 kilojoule per kg Kelvin. When temperature changes, the entropy will be lesser, so it should be say 150 or something, 150 kilojoule per kg Kelvin. So here the entropy change is delta S is final minus initial, 150 minus 200, so which is minus 50. So there is no heat transfer or there is no work transfer in this system. The entropy, only the entropy has gone down by 50 kilojoule per kg Kelvin or 50 units. So from this we can say that this system is not possible. And similarly for the given system, based on the entropy sign, we can say if it is possible or not.
Okay, thank you, sir.
Okay, so for the first stream we have calculated the entropy change is positive, which is 0.493, and similarly for delta S 1 2 3 we have Cp ln of T3 by T1 plus minus R ln of P3 by P1. So this is 1.005 ln of T3 is we had 270 Kelvin by 300 minus R is 0.287 ln of 1 by 4. So this is 0.292. So this is also positive, 0.292 kilojoule per kg Kelvin. So that means the total entropy will be entropy total is equal to delta S 122 plus delta S 123, and that will be around so that will be like 0.786 kilojoule per kg Kelvin. From this, okay, so since the sign is positive, I can say that the system is possible.
You can show the previous slide, sir.
Yeah.
Sir, these formulas are delta S and these are same method, same like this, sir, for this type of questions.
Sorry, what equations?
Delta S, integration of TS.
Yes, yes.
How to take this? Means the method is same for this type of questions, sir.
Yes. So when there is a flow process, so here the system has a flow of air, right? So whenever there is a flow of air, we will take control volume. So this system, we say a control volume, some air comes in and goes out. We are not worried about the exact mass of air that has come in and gone out. We are only concerned about the about this volume, what happens at the boundary of this volume. So this type of problems are flow problems, and in flow problems we will generally deal with this expression dH minus VdP for the Q. So delta S is as per this integral, Cp ln T2 by T1 minus R ln P2 by P1. So for most of the flow problems it will be like this. And if it is a non-flow problem where it is a piston cylinder arrangement or something, then we will have from the first law expression, like so if we have a piston cylinder arrangement, then Q is delta U plus P dV, and so this is T ds, this is du plus P dV, and ds can be calculated as Cv dt by T plus P by T by V into dV. So here we will have Cv ln something plus V into ln of something. Sorry, I think it will be R here. And here we will have V2 by V1, something like this. So this expression we will generally use it for the non-flow problem, and that is for the flow problem.
Okay, thank you, sir.
If you have any other questions, I can take it now.
Sir, this video available, sir?
Video will be uploaded to YouTube, and the link will be put in the NPTEL portal. You haven't seen the videos earlier?
Yes, sir. I see.
Okay. In the NPTEL portal, in the left column, there will be different weeks, right? Where you can choose the week and then choose the topic. Like maybe week 10, it is entropy 7, entropy 9, similarly. And similar to that week level in the menu, you will have something called problem solving session. If you click on that, you can open a Google Drive document, and in the Google Drive document you will see links of me and the other TA doing their video, our video, and this notes as PDF also will be there with the link.
Sir, one more thing. Sir, if I get any doubts and clarifying as possible, sir.
You can put in the discussion forum. You know about the discussion forum also, right?
Sir, I don't know how to open that one, sir.
Okay, let me quickly show that. So here you can ask a question on the top. If you click on ask a question, you will be directed to a discussion forum. So this will be a Google group where you can ask your own question. So you can start a new conversation and then ask a question here. And for the problem, our videos, this is you have to click on the problem solving session on the left side, and and again this problem solving session here, and then this, there will be a link to a Google document. So these are the links of the different week problem solving sessions. So this column B has the YouTube link and column C has the presentation link. For example, if I click on this one, week 10, it will be redirecting to a YouTube video. So this is I think this is my last this is my video from the last week. And okay, this will be loading. And similarly, if you go to this Google Drive, there are different notes for different weeks. For example, 9th week note is like this.
Sir, using this notes and lecture video for preparing a GATE exam, benefit, sir?
You should actually look into the syllabus that is given in the GATE and here. So I haven't seen the syllabus for GATE and this exactly, and I haven't made a comparison. So you can make a comparison and see if both are matching. If there is something missing in this course, then you have to go and learn yourself. Otherwise, if both the syllabus are matching, maybe this is a good starting point. Then you can try to solve some problems from the previous question papers, and then you will gain confidence attending GATE exam. And I think there are also some GATE portal in NPTEL where there will be different previous year questions solved by some people, and it is put as a video. You can also look into those things.
Yes, sir. I following that also.
Okay.
Thank you, sir.
Okay, I think we have only 3 minutes left. If you have any questions, we can solve. I think if I take the next problem, it will go for a few more minutes.
No, sir. No doubt, sir.
Okay. Okay, then we will close the session.
Sure, sir.
Yeah. Okay. Thank you for attending. We will see you in the next week. I will close now. Thank you.
Sir, when the next session, sir?
Next session will be same Friday 6 to 7 p.m. and there is another TA who is conducting at on Tuesdays.
Okay, sir. Thank you, sir.
Yeah, you should be getting a reminder mail every time, right?
I
Every week. You are not
getting.
Sorry.
Yes, sir. Getting, sir. Information I getting.
Okay. I think it will be Tuesday. I don't really remember the time. I think it's around 7 to 8 p.m. or something. You will get the reminder on Tuesday. You can attend. And my next
yes,
session
sir.
will be on Friday 6 to 7. Next Friday 6 to 7.
Okay. Thank you, sir.
Okay. Thank you.
Okay, bye, sir.